Okay, we begin. Okay, Monday students, yesterday the connection was not good, so we'll meet again separately on Skype or on the class, and we'll do that lecture again. But that shouldn't bother you today, because what we will do today is somewhat independent from what we were talking yesterday. Okay, so today we'll look at designs of collectors. We'll start with some pictures, then we'll go back to the science and engineering of this, and then again go back to these pictures. So, this is the first picture that you are seeing. This is one of the oldest power plants in California. I was mentioning that in the last class. This is the Mojave Desert. If you look at the geography, you will find that most of Southern California, east of Los Angeles and going up to Arizona and into Mexico is a desert with hardly any rainfall there and very little clouds or dust, and so that is in a way an ideal place for putting up solar power. Temperatures in that part of the world are pretty high, like ours. Summers 40-45 degrees Celsius is not uncommon there, 47 degrees Celsius in summers. It does not snow though. So, this is the type of thing that I was talking of last time. What you see here is this is central part. There is a building there, which is a plant room, where you have the turbines, condensers, feed water heaters, pumps, instrumentation and control room, everything is sitting in this building here. This is the tower, and the top of the tower you see somewhat glowy. This is because this tower is like a cylinder, where the outer surface of the cylinder has tubes wound on it, through which the fluid, whether it is an oil or steam, that is being passed. I think in this case it is steam. So, you are pumping in compressed liquid and it goes through this set of coils and becomes superheated vapor. This cylinder is being heated by sunlight reflected from each one of these little things, which is a mirror. As I mentioned, the heliostats. So, every one of them has got an independent control, and depending on the position of the sun, they keep reflecting the rays, so that they hit this cylinder in the middle here. If you want to get some idea of what would be the dimensions of this, what do you see? There is a door over there. So, that is about like 2 meters or so. So, this whole thing will be a more like at least like 20 meters in height and about maybe 5 to 10 meters in diameter. So, that is the size we are looking at. I think this plant was rated at 100 megawatts, I think. So, this is all that you are seeing is for 100 megawatts. It gives you an idea of the number of reflectors that are there, these heliostats. In the same picture, you can see little close up of these parts. That I do not have the scale on this, but across this distance could be like from here to there, it is like a circular array. This could easily be of the order of about a kilometer. So, we are looking at very, very large land on which the reflectors have been put up, and all of this to get a peak of 100 megawatts. When we say 100 megawatts, it is not continuous 100 megawatt generation, but only in the peak times. Mornings it is less, afternoons it is less, night of course it is 0. So, this is one picture. This is probably the world's oldest plant in that sense. Okay, there is some other picture there. Okay, this is a more recent power plant from Spain, I mentioned last time. I think this is the one that ran 24 hours continuously producing electricity, and you can see here that they have one set of heliostats sitting there, second one over here, and a third little one sitting over there. And so, what they have done is that there is a tower over here. The design of this tower is because of all structural requirements and also wind loads and other things. Besides, of course, that it has to do all the heat transfer that we want. All these are your heliostats, each one of them there, and they are all reflecting sunlight onto one side of this tower, and that produces the heats of the oil, the thermic fluid, which stores it in salt bath, so that at night you can draw down energy from there, and a balance is used to generate steam and drives steam turbines. So, this is among the newest plants. This is half the size of this one, and even then you can get an idea that this is a road. This road width is likely to be about what, 6 meters or something like that. So, if this is 6 meters, you can imagine what is this entire dimension. Okay, what do you think this is like? The 3. So, each one of these bands there, they would be of the order of about 6 meters, 10 meters, somewhere there, and you have at least 30-40 of these. So, 40 into about 10, 400 meters this way, 400 meters that way. So, it is a fairly large area. Then there is okay. So, that was the first type. This is the other type of power plant, which we will discuss in a few minutes. What you see here is a shape like that, and this is a straight thing, and it is so big you can't even see the other end. And in this, we are focusing the sun rays at the focus of this particular shape, and that is focusing on this tube running there. It goes straight like that, and through this tube we pass water or thermic fluid to heat it up, and then collect all of that, generate steam from there, and then you generate your steam, get a steam turbine operating from that point. So, we will look at this in a minute, but you can see that all these shapes, what do you think all this thing is? These are all pipelines, because each one of these you got to take the liquid, heat it up. You do not want to put it at one end and keep taking out at the other end, because you will get heated too much, maybe will damage the material. So, you heat it up to a point where you got the temperature that you want, then take it out, and at another point you introduce fresh cold liquid, goes some more distance, comes out, again put more liquid, goes some distance, comes out. You collect all of these parallel paths, and then you get your total mass flow rate of hot liquid that you want.
So, the pipe losses will increase substantially in this?
Well, there will be both two things that in any piping system, which is your frictional pressure drop, which you have to overcome by your pumping system, and heat transfer through the insulation. What you are seeing, all the shiny thing, is the pipe over which there is insulation, over which is the aluminum cladding. So, you are not really seeing the pipe anywhere. This is the aluminum cladding that you are seeing this, and that is, you got to factor that in when you do the engineering of this. There is no running away from it. You have to do it, and at this point everything is being collected, and then they drive the remaining machinery from here. As the sun changes its azimuth angle, this whole thing is mounted on one support at the end, and this entire length is its angle is adjusted, so that the sunlight is focused on this tube in the middle. So, that is an automatic tracking system that they have. We will look at the details in a minute, and let us see if I have any other pictures. Yeah, there is a close up view of the same thing. You can see the shape here. This is the shape, this part, and that is a parabola. So, this type of a collector is called a parabolic trough collector, and in the center this is a pipe which is supported, this is a width of one trough. Behind that is a structure which is mounted on a system whose angle can be adjusted, and then it is through these pipes, through a flexible connection, that the water has to go in. Remember, this pipe is also going to turn along with the collector. So, the connection of the inlet and outlet pipes into the header has to be flexible. So, at each end you will see there is a pipe running around either over the ground or under the ground there. Okay, this is just your heliostat, flat plate. These reflectors are all flat plate reflectors, at the most slightly given a trough.
In this case, why do you have so much space between?
So much space between
Between each reflector.
which space? This one?
Between them or between those two?
Between
Two adjacent.
two adjacent ones. See, what is happening is you got two flat things. In the morning they will all look that way. So, you do not want the shadow of this to come onto this. In the daytime they are fine, they are both looking up. Afternoon when they both tilt, you do not want this shadow to fall on this one. So, when you space it, this becomes another consideration. Same thing with the rows, one behind the other. And what we have not mentioned here is that in between them you have enough space, at least like 2 meters or so, like just like this road, maybe slightly less than that, for a maintenance vehicle to go through. So, if you may say that that space is not being used, but you have to give away that space, because otherwise you can't do repairs on it, you can't do maintenance, you can't even clean it. How they clean on this is not shown here, but in the other power station that I showed, the Mojave Desert, they have a robot on trolley that goes the whole length of one of the reflectors and washes all of them, and in dust storms they have to take care of this. All these things are not so much of a problem in Spain. It is not so dusty or so smoggy as we have here. You can just I am just doing a search here in Google and getting a lot of these pictures. So, you can do the same thing yourself, and I will show you the third one also. Let us see if it pops up. Okay, here is another type, this one. Okay, what you are seeing in this, is it okay? This is a structure. On the other side you put a steel structure on it, and on the other side of this, or you can see the small panels over there, this is a reflector plate, and all these things point to the sun, and they are focusing the sun rays onto this little thing over here. And this particular picture that you are seeing is for a solar cooking unit. There was one such thing right here in IIT Delhi campus for cooking chapati, but in the end those people are using it only to keep their food warm, because the mechanisms in this, they are all completely mechanical. So, the whole tracking of the sun is mechanical, but it did not work that well here, but this is for cooking purposes, this is not for power generation. I do not know if you can see this picture. Okay, this is, while we are at it, I just show you this, a very small image. Here is a factory or an office building. On top of this, these dishes have been put, And with this, what one can do in a building like this is not use it for power generation, but use that hot water for either process heating. Suppose you have a laundry or a kitchen in that, say a hotel or a hospital, you can use that steam for that purpose, and you can also use some of that heat to air condition the space. Yeah, this is the one I wanted to show you. Yeah, this is called a Scheffler dish or a Stirling dish, and what is being done here is that there are lots of these flat panels, small ones, which have been mounted on a larger frame which has a parabolic structure. And we do that so that this manufacturing cost of each one of these panels is not very high. Making a flat reflector is much easier than making, say, in glass or aluminum and giving it a parabolic shape. And what you say is that, look, why do I need that much of a parabolic shape anyway? Because even if the energy is concentrated on this much, say a square of 10 centimeter diameter versus 5 centimeters diameter, I am quite okay with it. So, that is what it does. This whole thing has a double axis tracking mechanism, which is powered and it is automatic. So, it keeps track of the azimuth and the other angle of the sun, and all the sunlight is being reflected into this here. We can't see this part, but it is a hollow cavity inside, and inside that cavity are a bunch of pipes through which oil or water is being circulated, and you produce hot oil or superheated steam with this. And then this oil is again pumped in and pumped out, and like that you collect it from many of these dishes, and you can even generate enough steam to get a power plant running, or you can use this for process heating also. The size of these dishes is typically 3 meters by 3 meters. Some big ones will be 5 meters by 5 meters. Okay, so I think we will leave this at that, and we come back to what we wanted to learn. So, this is where we were yesterday. We said, how can I concentrate solar energy onto a surface, make it hot, and then use that energy. Let us having shown you something, I told you that generating electricity from solar thermal process, which is what we are looking, is one of the ways in which we can harness solar energy. Then you have direct conversion through photovoltaics. You can use that heat for heating purposes in a process. You can use that heat for running air conditioning plants, and which is the most efficient converter of solar energy into something useful. Which is the most efficient way by which solar energy can be harnessed. Remember, nature does everything the best. So, what does nature do with solar energy? Photosynthesis. That is absolutely the most sophisticated process by which you can harness solar energy. And if you look at today, there is a lot of research, very fundamental nature going on about how photosynthesis takes place. Whether it's engineers or biochemists or chemists, people are looking at it very, very closely, hoping that you can then mimic that to produce various things. People are also trying to look at that and learn from there how at that little level you can make things happen, and that way make the solar photovoltaics much more efficient than what they are today. So, this was the structure of that first picture we saw. This is a structure, a tall tower. On top of that, there is a cylinder through which all the tubes are going, and the external of that cylinder is being heated by the solar rays. As the sun moves, these mirrors, they have tracking, this is done through an automatic control system, and it keeps on adjusting itself, so that the sunlight is always hitting the area where you have got the liquid moving around. Surface temperatures here can get very, very high. Theoretically, what is the highest temperature to which you can take this surface? So, sun is at 6000 Kelvin, about 5800. So, theoretically you can produce a temperature of that type by harnessing solar rays, and there is at least some manufacturing practices where this is the only way you can produce a material, because if you want to say heat something to 3000 Kelvin or melt a material or fuse a material or do something at very high temperatures, if you are going to do it in an artificial way, you will either have the choice of electricity or plasma or burn of fuel. In every one of those cases, you contaminate the substance that you are working with. Focusing solar rays, and especially this box were in vacuum and you kept your processing material inside, then that material is going to be heated by solar rays. You can get very high temperatures and there is absolutely no contamination. So, ultra super critical, what you may call clean technologies for material processing ultimately go to solar energy. And there is one such plant in France, quite old one, where by doing this they could, you take a stainless steel plate about 25 millimeters thick, you could drill make a hole of 25 millimeters diameter in a matter of few seconds. That is how all this focusing will produce. So, this external surface gets hot, it is not 5800 Kelvin, but easily going up to 800 to 1000 Kelvin. Which is why in that picture you saw the whole thing was glowing. You had heated it almost as if you were going to do a forging experiment with this. And that puts up a new challenge for heat transfer people, that when you are trying to put radiation on the surface, your objective is that, say this is the surface, behind that are tubes through which the liquid is flowing, and what you have is, this is a solid metal, this is another solid metal. And now you ask the question, how can I predict how much area I require, what is the heat transfer rate I will get, and that will tell you what is the maximum temperatures that you will get. So, you have to do a modeling of the solar energy which is incident on this. So, this is radiation coming from the sun. This thing is also looking to sky, which is 0 Kelvin, and it is also looking to the ground, which is 300 Kelvin, say. So, those are all the surfaces that participate in radiative transfer with this particular surface. Minimum, you can add more and more things like the mirrors themselves or buildings, and that will complicate it, but 3 is bad enough. Then this surface got hot, and because of convection this surface starts losing, giving its energy to the air outside. And if you have heated something to that higher temperature, say 800 Kelvin, the amount of air that will go past this and take away energy from this is going to be very high. So, you need to worry that I am heating it very well, but I am losing also a lot of energy to the ambient air because of this. After that, there is conduction through this metal, then there is contact with the tube, that is the conduction process, conduction through this tube, and finally convection to the fluid inside the tube. This is a fairly challenging heat transfer problem. A lot of people have done work on it, but as more and more designs come, more and more materials become available, people are making the simulations continue to be done in many ways. So, this is a central challenge on this part. The big challenge is on this side. I mentioned last time that we are saying very happily that there is a mirror on which the solar rays come and they get reflected, but thing is, how do you make this mirror that you saw in those photographs? The old thing was that you make it out of glass. Glass is still cheap, you can make the shape, polish one surface which is going to be a reflecting surface, and then coat it with a reflecting material. It is never that the back side of the glass is the reflecting material. Say this is the glass thickness, the reflective coating, which is only a few microns thick, sits on this part. So, the solar incident radiation does not actually go through the glass. So, it comes on the top here and from there it gets reflected off. This continues to be a big research area, but what you want to do is that these wavelengths, they are coming in all the wavelengths, predominantly infrared. Most of the energy from the sun is not in the visible wavelengths, but say about 0.7 micron is the end, say 1 micron to 100 microns, those wavelengths is where majority of the energy coming from the sun is concentrated. So, you need to reflect those rays at those wavelengths. So, a surface that looks very reflective to the human eye is basically looking at 0.3 to 0.7 microns. So, what it does with visible wavelengths may not be the thing what it does with these infrared wavelengths, and that is where it is a really big issue, because working with this whole range of IR wavelengths makes the problem really complicated. So, this surface material has to be chosen in such a way that is a good reflector of IR. You can coat glass with it, and as you are going to put it out there for days after days, weeks after weeks, and for many years, you do not want this coating to come off. You just look at a mirror that you have in your bathroom, and you find that with no time at all the coating at the back becomes bad. So, getting a very high quality coating is not so easy a task. The third thing that happens is it gets heated, and that heat could cause heating up of the glass and the coating. So, now you have to treat this whole thing as an independent heat transfer problem, and say that this is a solar radiation coming at different wavelengths. Reflectivity itself rho is lambda dependent, unlike visible wavelength where say reflectivity is 1 or 0.95 or something. That is not the case over here. At 10 microns it may be very high reflectivity, at 50 microns it may be very low, at 100 microns it may even be 0. Then you say what is the absorptivity of this surface at these wavelengths, and then you say that from here, because the surface is going to get hot, there will be convection back into the atmosphere and conduction into the glass. And then you got to solve this whole problem to get a temperature distribution, get the stress analysis on this, and say what is the distortion that is going to happen in the glass. This distortion increases during the day, becomes less at night. So, the glass is going through thermal cycling as well, just like this thing is also going through it. And like I mentioned with the steam turbines last time, all these things which are subjected to thermal cycling, this is going to be your main cause for failure of these components, and this is a problem that has not been solved yet. The only way we can do it is of course make some things, run it for many years and see what happens, which is like that Mojave Desert plant. It has been running for over 30 years now. So, by now they would have seen how many times the glass breaks, and it does not matter that technological advances did not take place. If they used a mirror designed in the late 70s and the new mirror came in the 90s, they could just replace that mirror and put this new mirror and see the whole thing working again. Okay, so this is a big challenge. Material science, mechanical engineering, manufacturing, all of these comes in, and as I keep mentioning it again and again, you got to have a way by which you are going to keep this clean. This is not easy. And many of the alumni who graduated 8-10 years back and have done a PhD, quite a few of them are actually working on these problems now, both in a company or with a research laboratory and setting up new power plants like this. Okay, the second thing that I showed you was the parabolic trough collector. And the pictures, as you saw, what it said, that we make a frame, that is a steel frame that you make. This frame is say at some point mounted on a shaft. The shaft is mounted on bearings, and you can adjust this thing this way or this way. And of course, this bearing finally is grouted and you have a foundation. The sunlight comes on this, and the entire thing is focused over here. So, this is coming and hitting this, this is coming and hitting this, this is coming and hitting over there. So, what I have drawn is a cross section through that picture that you saw, and this thing runs normal to the plane of the paper hundreds of meters. 300 meters, 500 meters, 1 kilometer is typical. As engineers, we cannot make anything that long. So, we make this particular thing in units which are say about 2 meters, 3 meters, 5 meters in length, and put lots of them in parallel and connect all of them up. So, what happens in this case is you focus the rays on this central tube, and now you do not need a tower. So, one of the advantages of this system is that cost of putting up a big tower is gone, that is number one. Number two, you do not have so many independent controllers that are adjusting each and every one of those heliostat reflectors to put the energy onto the tower, that is gone. So, again cost saving. All you did was make one thing and you have only one adjustment, which is also pretty simple. So, yeah, yeah.
Sir, generally we see that we have studied in radiation that for practical purposes all the surfaces are supposed to be diffuse surfaces. So, if the surfaces are diffuse, then I mean how are we going to get complete focused incident radiation?
Okay. What I did not mention that in all these pictures that you have seen and all the earlier things also that we have seen, all these mirrors, our first criteria is that we want this reflection to happen the way we learnt it in 8th standard in school physics. So, all these have to be specular reflectors. This is absolutely essential. We cannot do away with diffuse surfaces as reflectors. So, in addition to all the other properties that I mentioned, this is of course central to the technology being successful. And remember again what I said here, it has to be a specular reflector in infrared wavelengths. Visible wavelengths is not good enough. And to minimize, as you have learnt in manufacturing, there is no such thing as a perfectly smooth surface. Every surface that you go into a very microscopic way, every surface has this type of a texture, and that is decided by the center line average, and that is of the order of you can make 4 microns, 16 microns, 1 micron, 0.4 microns, like that. So, you actually try to make this into a polished smooth surface going well below 4 microns. 4 microns is a rough surface for this. We make it even more smooth. Just as a way of information, now that we are talking of reflecting and reflecting surfaces, one of the most sophisticated mirrors that has been made was for the Hubble Space Telescope. And those of you who read a newspaper about 2 weeks back, one of the biggest astronomical telescopes was inaugurated somewhere in the US. That telescope does pretty much the same thing what we are seeing here, except that it is looking at night and focusing light coming from stars. The critical thing there is this one. Those mirrors are a single piece mirror. Here we have the flexibility as engineers to make it to any size we want and put more of them together. Even if the focus is off by a few millimeters here, we really do not care. The heat transfer tells you that, look, why should I concentrate all the energy in a very small area? Even if it is over a big area, it is okay, because my convection heat transfer would require a bigger area anyway. So, we are okay with it. In astronomy mirrors, those are telescopes, that is not the case. These mirrors are single piece mirrors, and the biggest mirror until some time back was a 4-meter diameter mirror. Now, I think they made a 6-meter diameter mirror. So, 6 meters is like the width of this room, almost half the width of this room, and this is a single piece mirror of glass with no defects in it, and finally, the top surface is polished and finished to something much smoother than 4 microns. It goes well down to something like what we call lambda by 10, lambda being the wavelength of yellow light, that is 0.5 micrometers. So, if you are going 1/10 that wavelength, you are looking at 0.05 micrometers. If you are going lambda by 20, you are looking at 0.025 micrometer center line average of this surface. So, telescope mirrors and mirrors used with lasers, they go like that the surface roughness is way below what we see everywhere else, which means that polishing them is a challenge. And the next challenge that comes is that this mirror, because it is 4 meters diameter, you can't just keep it. Because of the heating and the room temperature changing, this will change its shape, and for astronomy purposes, the change in shape is bad enough that you cannot do anything with it. So, you not only have to control the temperature of the environment, which is not very easy, but each one of these mirrors is not supported on a steel frame, but what they do is take this big mirror and support it on like 600 individual points. Each one of these can be adjusted up and down by a little stepper motor, and what it does is that if this mirror has deformed, you first put a light on it, find out what its shape is, go to an algorithm which does the back calculation of the stress analysis and deformations, and say which one of these has to be pushed up, which of these has to be pushed down, and with that little pushing of the glass, which you do not even see a deflection, it actually changes the shape of the mirror and it comes back to what you actually want it for. Then you can start using it. Same was the story with the Hubble telescope mirror, but that is a much longer story, that is not for now. But yes, these are to be extremely smooth specular reflecting surfaces even over here. Glass is one thing I mentioned. The trouble with glass is if you make it thick, its weight goes up, the whole structure becomes heavy. You want to make it as thin as possible, 4 millimeters, 5 millimeters, 8 millimeters, you try to do it, but then when you put on this, nothing is absolutely fixed. This will also deform a little bit, and if you see any pictures, you can go to the web and see many pictures of these farms which have been in operation. Quite a few mirrors break by themselves because of thermal stresses. You got to keep changing them all the time. So, people said, why go for glass, let us do it in a cheaper way, and the big research that has been going on over in the country is with aluminum. Aluminum is cheap, it is light, and now the question is, I make the sheet out of aluminum, which is pretty cheap, but how do I put the coating on it? A coating which has got high specular infrared reflectivity. And even if you know what that material is, how do you make it stick to aluminum? This has been one of the biggest research projects in the country in the last 4 or 5 years. One such mirror has been developed and one company is marketing it, and they are in the market right now. But the race is not yet over. There is still a great opportunity to increase this whole aspect, the technology, and take it forward, put newer coatings, thinner coatings, make it stick and make it survive 11 months, 15 months, 20 years non-stop. This is the challenge. Remember, when you put this coating or put a coating on glass, you wash it, something happens. If you have glasses, what does the chap from whom you buy the glass, that shop tell you? How to clean the glass? इतने सारे लोग अनक पहनते हो, अनक कैसे साफ करना चाहिए? What do they tell you? Okay, they give a cloth, and what else did they tell you? They give a solution. Why? So that it doesn't scratch. You take your glasses, you think that there is dust, you take them off, take your hanky or any other clean cloth and wipe it. Those glass particles are nothing but SiO2, silica, most of them. The moment you pull it, that silica particle scratches your lens. In no time you will see lines over your glasses. That is the danger over here. That much of rubbing of particles on a mirror is unacceptable. So now you have a challenge, how do I keep this mirror clean? And we do not have an answer yet. So those of you who want to do innovation, like in your 202 course or other courses, you still have this thing going on for you. It has not been solved. So the parabolic trough collector, this is reflecting it, comes here. This tube is no ordinary tube. Now comes the next case. You want this tube Okay, so this is the tube. Let's forget, let's not worry what the metal was. This is getting bombarded by reflected solar radiation on half its side. The other half is not getting anything. So, first problem with the tube is that it is getting differentially heated, it is going to deform, that is going to be a problem. You got to solve that. But from purely a heat transfer standpoint, what should be the property of this surface as far as radiation goes? You have three properties that you can play with: absorptivity, emissivity, for reflectivity, transmissivity. For this surface, you said I want rho to be almost 1, I do not want any absorptivity or transmissivity close to 0. Nothing will be absolutely 0, some will go away. Okay, fine, does not matter. This is what we want here. What do we want here? Yeah? One, you would like to have good transmissivity, or second, okay, low reflectivity. So, you do not want this incident thing which with great difficulty you reflected here to get reflected off. So, this is a funny thing we want now: high transmissivity and low reflectivity. You do not want it to absorb too much energy also. So, what is happening is solar rays are going through this. As they go through this, the whole bulk material absorbs it. This type of a problem, which is called the participating medium problem, you have not learnt in your undergraduate heat transfer course, that is all postgraduate stuff. But how to compute how much this glass will get heated up, it is a different science to it. So, this is one requirement for this tube. Then what we do is, inside this we put a second tube. Through which the liquid is being pumped. Now, what properties do you want for the outside surface of this tube? Suppose we achieved our first objective and said most of the radiation that got reflected into this managed to get through this. Now, what do you want this glass, this surface to do? You want high absorptivity. So, alpha should be very high, you want rho to be small and transmittivity to be 0, and that means you put a metal tube, but coat the exterior so that it gets this property. You take ordinary stainless steel tube or aluminum tube or carbon steel tube, they will not have very high this. Yes, if the tube is rusted, very good. All rusted surfaces are excellent absorbers at all wavelengths. But then a rusted surface is not a very nice thing to have. So, we make this double wall construction and it absorbs all the energy, conducts it through the tubes and convects it into the interior. What do we want this middle space to be? This space we want it to be evacuated. Why? When this surface gets hot, this tube surface is going to be getting very hot. If this was exposed to the air, it would start losing energy to the air, and that could be quite substantial. 50% may not be an atypical number. So, what we have done is put this double hollow tubes and evacuated the middle part. So, when this tube gets hot, convective heat loss from here to either to this tube or to the atmosphere has practically been knocked out quite severely. And almost all the designs of focusing type of collectors have this structure. There are some of these here on our campus. You can see that there is a long straight tube in front of block 4 and block 5. They are all of this design. They are for water heating, not for generating hot steam for solar purposes. This tube, of course, is subjected to the high pressure of the water coming in or the thermic fluid which is going through it. So, this has to be mechanically designed strongly, and this whole thing has to be long, 3 meters, 5 meters, has to be put between supports, and at the ends has to be connected to the next adjoining tube in the same way. So, these are engineering challenges, and you got to find materials that can withstand this, and anything of those materials like hoses or things that you put, the biggest problem with synthetic and those type of materials is exposure to UV radiation. You take most plastics, keep it in the sun for a few days and see what happens to that plastic. It's a big problem. Okay, so this was the second design, and the last one, we are almost out of time, but I will just mention that this was the Schaeffler. So, what we did there in that picture that I showed you, we put lots of flat pieces of a reflecting material, aluminum or glass, one of those two, and focus that light into a cavity there around which there is a coiled tube going around. So, what you have done is that you got this solar radiation falling on this is reflected into this. We are not even bothered about point wise reflection. It is a big opening. This whole thing, as you saw in that picture, would be about like half a meter, 30 centimeters in that size. And this depth would be like half a meter or maybe even up to a meter. So, these rays are coming over there and you are reflecting it over there. And this is not a 1D thing, it is a double concave thing. So, it is a part of a sphere. So, all these rays come in and hit this surface, and this surface we make it black, so that it absorbs it. This inside surface becomes very hot, and through the tubes we circulate the oil or whatever the liquid is or water and take it out as hot stuff. So, it is not uncommon that you send in at ambient temperature and get oil up to temperatures like 400 degrees Celsius. It is a pretty good high temperature that we have. This particular shape is what you would have seen in radiation heat transfer as a cavity. And what is the property of a cavity? Suppose I make a hole in a, say, a material, a blind hole, no light comes out. So, if you put radiation into this, it gets absorbed there, then gets reflected, gets absorbed there, gets reflected, and finally, practically nothing will come out. And then in radiation heat transfer, you would have studied that the area ratio of this area to this area beyond say 10 or something like that, this surface, even if its own emissivity is say 0.8 or 0.5, it practically behaves that this surface, this opening behaves like a black surface. And this is a very powerful thing that is exploited in so many places, that if you want a real perfect black surface, a perfect emitter or a perfect absorber, you do not coat something with something, you make a cavity and you get that exactly what you are looking for. So, that is what this thing is doing. It is absorbing most of the radiation that is coming into it, very little is being lost, and because it is inverted, what is happening is that the air gets heated, it remains in this, and to get out, that air will have to get so hot that will then have to start coming out from there. So, if you maintain, if you do not go to that condition, then you are pretty much sure that the hot air is staying inside this. Your convection heat loss to the surrounding air has also been knocked down. On the outside, of course, you put insulation, and that way you are able to get hot liquid from this type of a collector. There are some NGOs in different parts of India who made this thing with locally available material. They just made the frame with the local chap, got some ordinary pieces of glass, coated it and put it over here. The local fabricator made this, and they were able to get a good deal of heating, and they went up to sizes like 3 meters by 3 meters. This is quite a achievement there. So, I will close on the point that all these things have to have worried about one thing beyond what the heat transfer and all this was. First, seismicity, and second, and the most important part, is wind loading. I have not talked about it, we will not go into this, but you can go make a small wind tunnel and put these things together and see if the wind is blowing some way, how does the presence of one plate or one parabolic trough affect the other parabolic trough. It could cause what you call there will be vortex shedding, and it will start periodic vibrations of all these things, and even though your static stresses are well below your safe limits, this vibratory loads that come on, it could collapse the whole structure. So, those are all the challenges before the solar community, and it is not that things are not happening. The last 5-10 years, lot of things have happened, and this remains as one of the biggest research areas in the country today also. Okay, so that we will stop here.